All right. Hello, everyone. It's 1:30, so I think we'll begin. Thanks for sticking around for this Friday afternoon session, kind of a experimental new thing at the CW, but we'll see how it goes. Um, so my name's Riley Clark, and I'm a member of the Transmitting Variable Star Science Collaboration, and I'm coordinating the software task force within the SC. And I members of the task force helping me out today, Sid Cheney and Tobias Sharon. Um, and to give a little bit of context for this session, 4 years ago, the TVS Science Collaboration got a grant from the Discovery Alliance to uh, run a software training workshop in which they actually hired software professionals from industry to come in and teach astronomers how to uh, scale up their software and teach us about modern software standards and practices, so we could apply them to our own work. And it was pretty successful. And after the workshop was done, some of us realized that the materials that they used for the workshop, which were very like professionally and well crafted, that these materials were actually open source, and we could take them and modify them and kind of use them how we see fit. So that's what so for the last several years, just about every year, we've been running some of these workshops. Some of them have just been within TVS, some of them have been for the wider Rubin community. But this is the first time we've done it at the CW. But before I go on, just a quick reminder about the code of conduct. And if you witness any code of conduct violations, please get in touch with Adrienne, Federica, or Jeff. And if any virtual participants, please mute when you're not speaking, and use the chat to request and unmute when you have a question. Okay, so if you notice the Slack channel for this session, I posted a link to the course materials. So this is an interactive session, and the hope is that participants can follow along on their own machine as we go through the materials, and hopefully join us as we learn how to write unit tests, use a testing framework called PyTest, and scale up those unit tests, and also start create a CI/CD workflow, a continuous integration workflow. So if you click on these materials, link here, will take you to our webpage. So we're going to start the first page in the schedule, which is called Setting the Scene. And so the focus of this course is going to be about test-driven development. So the goals here, the goals of test-driven development is to make sure that when we develop code, we're not only satisfying the requirements, but also checking to produce that our code produces the correct outputs and ensure the user is warned when those outputs are invalid. So to give an overview of the topics we're going to go over, first of all, I'm going to take us through the setup for this course, where we'll clone the repository locally, and then set up a virtual environment, and also set up a feature branch on GitHub. And in the next section, we'll talk about unit testing, how to set up a test framework, what kind of different cases we should test, how we can scale those tests as our software project grows, and then how to automate testing with continuous integration using GitHub Actions. So this is an intermediate level course, which sort of assumes that you already have a working knowledge of Python, command line interface, and some of the more basic tools that we use in software development. So with that, I'm going to go ahead and go into the next section, where we're going to be obtaining an example software project from GitHub, and then setting up our virtual environment. And if at any point something doesn't work for you, or you encounter an issue, time is limited, so we're not going to stop the lesson to help everyone, but if you raise your hand, either Sid or Tobias will come up and see if we can solve an issue you're having. Yep.
So just want to add that please, if you need anything, call us over. This is meant to be an informal session, and we hope you can follow along live. And Tobias and I will jump and come to you. So just want to so that everyone is feels free to call us over.
Definitely. Thanks, Sid. Okay, so the first step that we want to do is we want to download our software project from GitHub. So if we come down to here, downloading our software project, we have a link to the project repository. A new tab. Okay, so we have our link to the project repository. And I'm actually going to kind of split this off to the side so we can see materials as well. Okay, and so the first thing we want to do is create a fork of this repository. So this creates our own separate contained version of the project repository that we can work on independently and then merge back into the main repository. So if I click, so we want to click the fork button, and it's going to ask you to create a new fork, and you're going to want to choose your GitHub account here. I've already created a fork of this repo, so but you should choose your own GitHub account in the dropdown, and then do make sure you have the copy the main branch only check mark here, because we're going to be creating our own branches for this repository in just a second. Okay, so then once we've done that, we want to obtain a local copy of our software project. So I'm going to quickly navigate to my fork here. Okay, so then to create our own local copy of this repository, we want to do a git clone onto our machine. So I'm going to open my command line interface, which on Mac is going to be a terminal. Might be slightly different interface if you're on a Windows machine. But I'm going to go to this green button that says code. And I want to copy the link under the SSH tab, because if you copy the HTTPS git clone, you won't be able to push and pull from that repo. So we need to do it with SSH authentication enabled. So I'm going to copy that URL, and then in my terminal, I'm going to go back to my desktop just so I have it in a convenient location. So I'm going to do git clone, copy and paste that link. Okay, so we see that it's downloaded, and now I'm going to cd into that directory. So enter Python workshop example. Okay, so then I can see by ls, I can see some of the files we have in here. So it looks like we have a folder for some data. We have an IPython notebook, and we also have a folder called tests, which we'll look in a second, and we'll see that we already have some tests there, but we're going to add some new ones soon. Okay, so now that we've done all that, we're going to set up a virtual environment for this project. So the reason you might want to set up a virtual environment is so that you create an isolated version of your software that is not going to interfere with your global environment, so that you don't have conflicting packages interfering with each other. So the way we can do that in Python is we're going to write Python 3-m venv. and then we're going to give it a path to the virtual environment. So I'm just going to, since I'm already in my project directory, I'm just going to type venv again. So this will create a folder called venv in my project directory. Okay. So now, if we look at if we do ls-l, look at our folder again. So now we see that we have the venv folder here. But now that we've created the virtual environment, we need to activate it first before we can use it. So on Mac and Linux, we activate the virtual environment by typing source venv/bin/activate. And if that's done correctly, then you'll see parentheses venv next to the command line. That tells you it's activated. And then, if you're on Windows, it's going to be venv/script/activate. Okay, and we can verify that we're which Python version our virtual environment is using by doing which Python 3. That tells you the path to the virtual environment's Python distribution. And then when you're done working on the project, you can just type deactivate, and that in the command line that will deactivate the virtual environment. But we want to keep it active for now. Okay, so now that our environment is active, we want to install some packages that we need for our project. So we're going to do this using pip. So first package we're going to install is pandas. So we pip3 install pandas. Okay, so that's successfully installed. And then we also are going to pip3 install matplotlib. And if you're installing a lot of packages at once, sometimes it's quicker to do it all in the same line, which also works. Okay, so now something you might want to do for your project, if you want to make it easier for others to use your project, is exporting your virtual environment to an external text file. So we can do that by typing pip3 freeze arrow requirements.txt. Okay, so now if we look at our folder again, we have a new file called requirements.txt. And we can look at it by typing cat requirements. And we see that this text file has all of the packages and versions that we just installed. So then if anyone wants to use your project and needs to install those same packages into their virtual environment, they can simply type pip3 install-r requirements.txt, and pip will install all of the packages listed in this text file. Okay, so we have a couple more packages that we need to install. So let's go ahead and type pip3 install AstroPy. Yeah, AstroPy is a slightly larger package. This may take a second or two. Yeah, also pip is not the most efficient package installer. I've been using UV a bit. So UV is another package manager for Python, and it works very, 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 very quickly. Okay. So then let's also install JupyterLab. So most of you are probably familiar with JupyterLab, especially if you've been using the notebook aspect of the RSP. But JupyterLab is a integrated development environment, or IDE. which we'll be using to run our the Jupyter notebook in our project repository. Okay, and then once that's installed, it's a good idea to also update our requirements folder, our requirements document by doing pip3 freeze. So now the AstroPi and JupyterLab will be added to our requirements. Okay, so we've done some changes to our project so far. So if we want to check those into our GitHub fork, so if we write git status, we'll see that we have an untracked file, requirements.txt, and you might also see that you have a that the venv is included in your is also untracked. So we can use a file in our directory called git.gitignore to tell GitHub to not track certain files that we don't necessarily want to constantly be pushing to our fork. So if we open this, if we open our folder containing the workshop example, we can see this gitignore folder file here. On Mac, to see hidden files, you might have to push Command-Shift period, and then the gitignore file should show up there. And then if we double click it, we can quickly edit it, and we can add the virtual environments to our gitignore so that we don't have to worry about GitHub tracking that file. So I'm going to add venv, except it's capitalizing for some reason, and also .venv. And then I will save that file. Okay, so then that should be added to our gitignore. And if we do git status again, I guess it wasn't showing up for me in the first place, but we do see that it's been modified now. Okay, so let's go ahead and add those changes to our upstream repository. So we'll do git add.gitignore and requirements.txt. And then we want to commit those changes to our local repository. So we'll do git commit. I'm just going to write add new files. Usually want to choose a fairly informative commit message. Okay. And then it's also good practice to do a quick git pull before you push any changes, just to make sure your local copy is synced with the upstream. Okay, looks like we're already up to date. So now I'm going to git push origin, and I'm going to be pushing to the main branch of the origin repositories. Git push origin main. And now we've checked in our changes. So often when we add new features to a project, we want to create those features on a new a feature branch, so that we can isolate those changes from our main project repository. And then once we make sure everything's working on the feature branch, we merge those back in to the main branch. Yeah, so if I do git branch, see that we just have the main. There's a lot more detail here if you want to take a look at the materials later, but I'm just going to quickly create a new branch called develop, git branch develop. So now if I type git branch, I see that I'm still on main, but I have a new branch called develop. And we switch to that branch using the checkout command. So git checkouts develop. And then there's a shortcut where you use -B, and you can just create the branch and immediately switch to it. Okay, so now we've created a new branch locally, but we want to also make sure that branch is created in our upstream repository. So we can do that with git push -u origin develop. Okay. Sorry, just checking if I missed a step. Okay. Let me just double check and see if our branch exists. Okay. So sorry. So this branch already exists on my fork of the repo, but hopefully creating that branch worked for you. Okay. So then to take our changes that we push to develop and merge them and merge the development branch on top of main, we do that with git merge develop, and you should see something like this. And then finally, we can push those changes to our main repository using git push origin main. So that should get us all set up for the next part of the lesson. Okay, so for the next part, we're going to switch over to Tobias, who's going to tell us about developing software at scale, ensuring the correctness of software at scale. Thank you.
Hello, everybody. I'm Tobias. I'm a postdoc at the University of Toronto. And so, yeah, I'll start the next section, which is on the main topic of this session today, which is basically how to test your software in a rigorous and automated fashion. So let me go to the next. So the goal for me today is twofold. First, I want to convince people that it's actually like why you should test your software. And then secondly, show people how to actually do it, right? And I hope it's relatively, the answer to why you should test your software is basically you want to make sure that your software is correct, right? That's not too crazy of a statement. Sometimes when you have, a relatively small project and you're just working in one notebook, maybe you can get away with just like reading your software and eyeballing it. And maybe that's fine. But as soon as your project starts growing and you're importing from different modules that you wrote and you're creating a giant GitHub repository, I hope you agree that that quickly gets out of control and becomes more difficult, right? Something that I notice quite often is that once I'm working on some software and then I'm switching to something else and focusing on something else and I'm coming back to it like a month, 2 months later, I tweak something on this part of the software and then like something here breaks, right? And so clearly there's a better way to do this. And that's what we're trying to teach today. Some other questions that we're basically trying to answer while testing software is, like, does the code actually work the way we intended? And how can we convince ourselves that it's working the way we intended? And almost more importantly, how can we convince other people that it is working, right? Because hopefully you want other people to use your software. And how confident are we of the accuracy of the software that we are writing? Another good example that we added in here is this example right here, right? So like, just imagine you have a piece of software that is only 70 lines long. And if you are really, really confident that every single line is correct, so let's say you're 99% sure that every single line is correct, then that 70-line software will still fail half of the time, right? So clearly we need to do better. And so in this world of testing software, there's like 3 different types of tests that get thrown around quite often. We're going to focus on the first one, which is what we call unit tests. And unit tests are basically very small pieces or tests that test very small pieces of your software. So usually that is like one function or one method that you wrote, right? But I just wanted to highlight that other types of tests exist as well, such as functional tests and regression tests. But for the purposes of today, let's just focus on the unit tests. All right. So in order to start doing this, we're going to create a new branch first. And so let's open the terminal again. And And so I am just going to first do git branch to see which branches exist. So right now we have the main and the develop branch. And the develop branch has this asterisk next to it, which means that we are currently in the develop branch, right? In case you are not yet in the develop branch, you can just do git check out develop, and that should move you to the develop branch. I was already in it, so it tells me I'm already in develop. But yeah, and so then we're going to create a separate branch where we're going to create all of our tests. So that is called, so you do that by doing git branch, and you can get, I'm calling it test suite. And then I'm going to move to that new branch that I created. So doing again, git checkout test suite. Cool. And if I then wanted to double check if that works, I can again just do git branch. Oh, nope, typo. Git branch, here we go. So now we have a third branch test suite with an asterisk next to it. I hope that worked for everybody. Cool. So before we move on, we just need to ensure that we are actually in the environment that we created. So we not only have to be in the correct branch, we also have to be in the correct environments, right? I think we went through that just now. If you aren't, you just type like source venv/bin/activate. And you should see, in order to check that you're actually in the right environment, you should see this like venv between two parentheses in the beginning. Cool, so if that's all set up, then we can start a Jupyter lab. Jupyter lab, and you just launch it by typing it in like this. And then you press enter. It'll take a while to think while it is opening Jupyter lab, and then usually it opens up this new tab automatically in your browser. If it doesn't, you can actually go back to the terminal, and it'll have a link here that you can copy paste. So let me actually move that over to this side right here. And so we have launched this Jupyter lab within our folder where all the rest of our, where the GitHub repo is located, right? So you can see the different subfolders that we opened here, including the virtual environment folder that we created. And so we are going to go ahead and open this Python notebook that we developed. And so now, of course, in order to create tests, we first need code, right? And so we went ahead and created a bunch of code already. This can really be whatever software project, whatever project that you're working on. But right now, we're focusing on some light curves from Rubin. But this is a stand-in for anything that you're working on, right? And so I'm just going to go ahead and import some packages that we're going to use. Here it takes a while to load. There we go. Here I'm basically opening the data folder and seeing what's inside the data folder, which is just here again. I'm assuming that people already know how to use Jupyter notebooks. If you don't, essentially, you can imagine that every cell is just like a little piece of Python that you can run separately. But then here, let me see if I can make it bigger, maybe. Here we go. Here, what I'm going to do is I'm just going to load a bunch of that data that's inside our data folder into the notebook under this LC, which stands for light curve datasets structure. And I'm just going to look at it, right? And so this is a pandas data frame with a bunch of different entries and a bunch of different columns as well, right? So nothing too crazy. We have some Kepler data as well, doesn't matter too much. But the point where I'm going to now is that we are going to take one of these LSST data points, just a random one, and we're going to open it, right? So it's now in object_ID. And then we're going to basically, this might seem a little bit silly, this next step, but like we're going to take that entry of that data frame and manipulate the data a little bit so that it's structured in a way that's more convenient for us later, right? So what that means is I'm going to create a separate dictionary that says light curve, that it's just called light curve LC. Then I'm going to loop over all the different bands from Rubin LSSC, and just for that specific object ID that we selected and the correct band, just store that in our LC objects, if that makes sense, right? If it doesn't, this is not the main point of today. But what this essentially just looks like is that we can now do LC and then take our favorite band, for example, the G bands, and we just get a separate data frame of all the G band data for that specific object that we selected. Awesome. Okay, so now we're going to get to the fun stuff. This was a lot of setting up to get to the testing. But we also created a bunch of code that is within this LC analyzer models.py file. It doesn't matter too much, but that is the code that we're actually going to test today, right? And so we are first going to import the models, and then we're going to basically use or test this function that we wrote that is called max_mag, which stands for maximum magnitudes, right? Which, as you can imagine, just takes whatever light curve that you put in and returns one number, which is the maximum magnitude within that light curve, right? So if we run it, and this is, so we're doing LC for the G bands, and then we input the corresponding column name that corresponds to the magnitude, right? So if I run this, hopefully it should just return you a number, right? And so maybe you're convinced now that indeed the max_magnitude function works, but how do you really know that, right? Like, it's just giving you a number. It could be whatever. Maybe there's a higher magnitude in there somewhere, right? And now, of course, you can actually go to the .py file, see how it works, and you'll see that it is indeed just like, max, so it should work. But the point is that you don't know that, and this might be some more complicated function where that is not possible, right? And so then one way to test if this max magnitude function works is by just creating a mock data set, right? Which is what we do here. Test_input is just some bunch of random data that we created. And then you ask yourself the question, okay, if this is the input for my function, if I think it just takes the maximum value for the magnitudes column, what is the output that it should give me, right? And so that is what we note here. And then we basically can just do, well, if we use the max_mag function on the test inputs on the A band, then it should equal the outputs. And if everything went well, that should equal true. So great, right? So now we know that this particular function for this particular test that we just wrote works. So that's at least a little bit more convincing, right? That the max_mag function is actually doing what it should. One more example. So we wrote another function in here, calcstats, which is basically running over all the different bands that you have and using the max_mag function on all of these different bands, right? So let's just run that. And now we want to test of this whether this calcstat function actually works. So what I'm going to do here now is I'm going to create 3 different data frames, which represent 3 different bands. In this case, it's a bunch of mock data. I'm going to combine them into one dictionary, which mimics like the LC structure that we had before, right? So this is all the simulated inputs. Then I'm going to simulate what the outputs should look like, and then I'm going to test whether they're equal, right? And now if I run that, very anticlimactically, it says false. Now, that was on purpose. Can anybody guess why this was false? Any suggestions or ideas to improve this bit of code? Well, so one of the mistakes that I made is that we actually had a typo in here, right? So this is not supposed to be df12 max, but actually df2 max. And we actually made a second mistake that the maximum value for this magnitude band is not 8, but 9. And if you run it now again, it equals true, right? And so the point of this little silly exercise is just to show you and like hammer down that actually writing tests can quickly become tedious and difficult, and you might make mistakes that are really silly, like this one, right? And so just because a test that you wrote here equals false doesn't mean that your code doesn't work. that you're testing. It might also just mean that the test that you wrote doesn't work, if that makes sense. So yeah. Now you might also think, well, this is, this is all nice and fun, maybe. But it feels a bit silly that for every function that you're gonna ever want to use, that you need to dedicate an entire separate cell in your Jupyter notebook to test it, right? Surely there must be a better way for this. Because it also, looks a bit strange if you want to share it with more people. It also just says false, but maybe you just wrote the test incorrectly, and it doesn't even tell you what actually went wrong, right? So there must be a better way to do it as well. And luckily for us, there is. And so instead of writing, we just did all of this. Instead of writing individual tests in little cells, we can create a bunch of tests for whatever new function that we created, and test all these smaller functions, all these smaller tests together, right? And so when we collect and combine a bunch of tests, we create something that we call a test suite. And then we will use something that we call a testing framework to help us test the code that we wrote. And so the testing framework that we are going to use today is called PyTest, which you can just install through, I need to open a new, there we go, which you can just install through the terminal as well. But if I just open a separate terminal window, just because the previous one is busy running the Jupyter lab. So I'm going to first activate my new virtual environment again. And then PyTest, the framework that we'll use, is essentially just a Python package. So you can just pip install it like anything else. So you just do Python pip install PyTest. Here we go. Nice. We also just wanted to highlight that there's different testing frameworks as well, such as unit tests, but they're all great for different reasons. But we're using PyTest for today. And so what PyTest allows you to do is basically what I just explained before. You're able to combine a bunch of different separate tests that you wrote in one file. And then whenever you write new code and you expand your code base, you can just run that one single file and see if anything broke, which makes it super efficient, super automated. And hopefully it'll also tell you what went wrong as well. Yeah, cool. So we wrote one specific test before. So like we have a separate .py file, but when you're doing this from scratch, you'll create this yourself. And as you see, this is basically the backbone behind PyTest right now, right? So as you can see, there's like an import statement, but there's also two right now separate functions that start with test underscore and then a name, right? And then and so every little like function in here is basically a separate test, if that makes sense. And so within every separate test, you import what you are testing. So in this case, we're gonna test the max underscore mac function again from before. And then I think the rest of the functions should look relatively familiar from what we did before, right? So like you have your input mock data that you create, then the column name that you want to test, and then what the output should be. And then this last line might be new, right? So you write something that we call assert statements, and they're pretty cool. And so basically what that does is that if whatever you write after the assert statement is true, then nothing will happen and everybody's happy. If it breaks, it'll throw you an error. And so if the test fails, it'll tell you it'll tell you that it fails. And that's the point of it, right? And in fact, you can actually be more specific if after the assert function, you can say what exactly went wrong, right? So for example, I can be like mac is incorrect or whatever. And now if it breaks, it'll error and give me that message, right? Cool. So now how to actually use it. So this is the backbone, like I said before, of PyTest. But then if you, let's say we expanded our code base a little bit, we implemented some new features. If we now want to run all these tests, you just go back to the terminal and you write Python PyTest, and then you provide the pointer to wherever your .py file is located. So in our case, it is under tests and then test models. And hopefully, if everything went okay, oh shit. What did I do? Oh, tests. There we go. Should have tests for the PyTests. Anyway, so nice. So it very quickly ran the 2 tests that we implemented, and says that all of them passed, which is great. We're all very happy. Now, just to show you what happens if it's incorrect, let's say I messed up and instead of 7, I just put 4, which is incorrect, right? And then run this again. It'll all be in red, a little bit more dramatic, and then exactly say like 1 failed, 1 passed, and then give you the message that you wrote in the assertion. There's somebody with a question. Yeah, cool. So let's revert this back to 7 so that we don't mess things up. Here we go. Cool. So yeah, I hope that is clear. With the next 5 minutes that we have, we're going to do a little exercise. So we thought it would be really useful if you go back to the models.py file. As you'll see, there are a few more functions that we wrote, such as mean_mag and min_mag. And again, you can see what they do, but the point is, again, these are functions. Maybe there are some arbitrary functions, right, that could be in principle super complicated. And so you should go back to the test models.py file and just write a new test function that tests these 2 other functions that we wrote. And then try to run PyTest on the new test suite and see if everything works out. And if you have any questions in these next 5 minutes, please just like shout. Yeah. Oh.
Thank you very much. I was wondering how complex can this be made? I mean, can we also think about preparing some mock data sets to test all the functions if you are preparing a more complex pipeline?
Yeah.
So is this thing able to handle through the assertion?
Yeah, this can become very complicated very quickly. And so this is one of the reasons why we're only focusing on unit tests in this session. But in the beginning, I mentioned there's also something that we call functional tests and regression tests. And functional tests are basically, I think if I understand correctly what you're describing, so they're basically testing how different functions interact with each other and all of that, and whole pipelines. And regression tests are more like, if you change something, will everything work? If that makes sense. So
yeah, exactly. So a single piece of function itself can work.
Yeah.
The input cannot work.
Exactly. Yeah. So if you want to, it's definitely possible. It's definitely possible, but it becomes complicated very quickly. Yeah. Any other questions? Yeah. Oh.
And thanks. So what about testing for, this is testing for known input, right?
Yeah.
What do you do for the unknown inputs?
Yeah, that's a really good question. We do actually have some tests on some text on that further down the lesson. We're not going to cover it today, but this is an example of that. Is it not? Oh, here we go. There's some. Okay. So this is an example of that, right? So like, let's say instead of inputting your data frame into the max_mag, you just input some string, then it's going to error, right? So you can test for like errors, is what we call it. And so that's what this looks like. So that's one example of how you deal with that.
Can I also just jump in? So this is not included in the tutorial today, but you can also test for properties. So there's this package called Hypothesis, which allows for testing for properties. It's like, so some of you know, I was once working with distance metrics, and all distance metrics have a property where it should follow the triangle inequality, irrespective of whatever number I use. So the way this package works is that you just put the conditions that, oh, this inequality should exist for ABC, and every time it will randomly generate some ABC and test for those properties. So you can also use that if you want to, if you know what kind of properties you want, but not necessarily the numbers.
Cool, thank you. I think we have time for one last question.
Are there any resources in this tutorial or any other tutorials where you can find more complicated testing examples?
Yeah, I don't think we have more complicated examples in this tutorial. But I think if you were to just Google functional test examples, or maybe Riley, are you going to jump in?
Yeah, for these materials, for the purposes of instruction, we definitely want to keep everything as simple as possible, because as we pointed out, like this testing can get like very complicated very quickly, and unit tests, like by their very nature, are usually very like small and contained, and usually test individual components of your software. But I think, yeah, like if we expanded on these materials and maybe added some examples of regression tests and functional tests that Tobias was talking about, yeah, I think it might be good to show some examples of just how complicated it can get. Yeah.
Also, just quickly add that something else you can now do, at least when I learned about testing in general, you can go to your favorite package, see what they're doing. So if you use NumPy, you might be curious, what kind of tests do NumPy use? And it'll of course be complicated, but you can now probably just take a look and understand something. And that's always a good benchmark, I feel.
Cool. And I think with that, we're going to move on to the next part of today. And Sid is going to take over.
I think you can hear me. That's not my laptop. I want my iPad.
Just while Sid is getting ready here, did anyone write a test and get it to pass with PyTest? Okay, well, Sid, maybe we could go back for just a second and look at what the solution to the exercise was.
Yes.
Just really briefly. Yeah, so the example solution here is coming up with a new test where we're testing if there are negatives in the min-mag function, which we don't expect, right?
Cool.
Okay, take it away, Sid.
Yes. So, all right. Now we're moving on to lesson 2, which is scaling up unit testing, which, as you saw so far, it's like you're running individual tests, and even if you add them to the PyTest, you still wrote individual tests for everything you were working with. Hold up, there is a Jupyter notebook open, right? So yeah, so we wrote some simple tests like this, but this can quickly get out of hand, right? You can test for maximum, you can test for minimum, you can test for whatever, integers, floats, and you might have to write each and every test separately. And something you can see is that the code structure of this is not really very different. The only thing you're changing is the inputs or the operations for this particular example. So there must be a way to sort of combine this so you can sort of provide a bunch of different inputs, bunch of different outputs together, and use all of them at the same time. So that's where, and jumping back to the lesson. So the lesson, I should add, has a lot of details. So if you're confused about any one particular thing, this reference will always be there. You can go back to this. I'm gonna go over this and code it, but I won't go over all the text. So we use something called a parameterized function within PyTest, which allows you to write a bunch of tests at the same time. So if I jump back to the code, this is the test we were writing in the Jupyter notebook. Let me just change this to first import PyTest. And I want to replace test max mag with a single function. So I'm gonna, you know what, let me just keep this while we write this. So I'm gonna use pytest.mark.parameterize, and then provide the variable names I want to pass. So that goes first. So the first row is just strings of the names of the variables. So I want to pass _df, which will be something like this. Then I want to pass a column name, which will be something like this. And I want to pass an output, which will be something like this. So those are my three names. But because I want to make it general, I'm going to call it test df, test call name, and expected. And just give me a second. Note that they should be a single string. So test df, comma, test call name, comma, expected. And that's my first input as a single string. Then I'll open a list and actually pass the data frames individually. So that becomes something like pd.dataframe, and I'm essentially copying this. So for my first test, my array consists of this one. So that's the first element of this tuple. That's test df. Then what's test call name? For this, I'm testing A, right? So I'm going to write A here. So essentially, we have taken care of this. Test output, what's the output expected? That's 7. And so that's test 1 done. And we can remove the whole thing. But we have not taken care of this. So let me keep that. So that's the first one. The second one, again, a tuple, is the second data frame, which is pd.dataframe of zeros. And let me just fix the formatting, because formatting is important. And the second column we were testing, as you can see in this code, is call name B. And let me actually maybe increase the size so it's easier to see. And so the second one we were testing is column B, followed by the output, expected output, that should be 0. And that is my second test. And that's all I want to pass. So I'll close the square bracket. So that means this is the first test, this is the second test, and the first, second, and third items become test df, test call name, and expected, respectively. Okay, so this is just something we call a signature, where we're adding this at the top, which is, so this parameterize itself is called a Python decorator. So you can read more about what the concept is if you want. There's tons of different examples, AI, non-AI, depending on your pick. But essentially, it's adding some functionality to the functions you're already using. So this is just something you're adding to the default function, which let's make a general version called test max _ mag. And let's call test df, test call name, and expected. And note how these are the same variables which we wrote above. So those are the ones that get passed. And following that, then this is just test max functions, and from LC analyzer, I forgot to close the string, from LC, so very similar to this. Let me remove that. And it's asserting that your testdf test call name is equal to expected. So just and now we can keep that. But yeah, so now we have essentially written a single test which does what both of these were doing, because we are passing two different variables, two different sort of data sets at the top itself. So this is good. We have successfully, well, actually, I haven't checked it, so let's run it. And I'm going to use the terminal within Jupyter Notebook. So let me drag and drop it to the right. And that's the test we just wrote. And as earlier, because I opened a new shell, I want to activate my environment. So I'm back in my desktop, which is where Riley originally made the environment. So source venv /bin/activate. Made some typo. cd venv. Was it not here? Okay, I see. That might be the problem. So this one, let me just clear it then. Yep, we're in the test. So venv is already activated. So let me just run python -m pytest tests. Is that correct? Yes. So you can see that it still ran two tests, but even though we just gave it one function. And so now if you wanted to, you could also add another test and say you want to test 1, 2, 3, and check that the maximum of C is 3. And just by copying the data format, that should run 3 tests. So you can see that works. And then now if you make some error, so now if you change the data and you run the test again, you see that there's errors. So we just learned how to sort of write a single function instead of many functions. And now we can easily recreate the tests for the maximum magnitude. But let me save this so that it works. Any questions on this? Any difficulties on this? Thank you. So let me add all the tests we just wrote. Test models _py. I made the same mistake where it's tests added, and then I can see that what the status is by doing a git status. I can do a git commit edit param tests, and we can also push it. Not origin. Test suite. Maybe I don't need to push it, right? That's okay. So moving forward, so we have seen how we can use PyTest parameterized to write multiple tests together. One more thing, which I think is quite helpful, is being able to use get a coverage report. So coverage report tells you how many lines of your project have you already tested, and so you can see what you could do more, what you could do less, like what the coverage looks like. And so the way to run that is a python -m pytest -- coverage is equal to lc analyzer dot models. So we pass the exact Python script we want to check the coverage for. So that is this project lc analyzer dot models. And let's do a term missing, so it reports just the tests that are missing. Hold up. I see. You're right. Sorry, I forgot. So that's a separate package. So pip3 install PyTest coverage. And once you're done with that, this should work. Let's ignore the term missing. And yeah, so I just did a Python -m PyTest coverage of LC analyzer models and gave it the test file. And it shows me what the coverage looks like. So there's statements, 11 statements, of which 3 are not really checked. So then you can add more tests. You can ensure that everything works as you expect it to. Something I really like is being able to generate a Python, an HTML file version of this, where you can do something just like before, but you can also add a curve report. You can't see. Yeah, curve report is equal to HTML, and that will write an HTML file into your project, where now, say if I just open this in terminal, in the Finder or your file directory, you can see that it generated a bunch of HTML files, and you get like a good coverage report. You can click on files, get an interactive report about what's working, what's being tested, what's not being tested. So the red lines are the ones that have not been ran by the code itself. And so you can see that 73% of this file has been tested. And so you can then write more tests. So now you're sort of aware that if I make any changes, all of these files, all of these lines will be checked. So I think that's quite helpful. So going back, the exercise, so there's another exercise you can take a look at. It's just about adding other tests, like you can make a single test for mean, et cetera, et cetera. So, and at the end, you can also read a section which I had added as optional about testing intermediate indeterminate output, as well as package-specific asserts. And those were the ones which Tobias also mentioned. So if you want to make more general tests which test for not just equality or even just specific values, you can take a look at this. But I am, in the interest of time, going to jump to the next section, which is, I think, also quite pertinent and has been very useful to me. But before we do that, any questions on this? Any broad thoughts, ideas, things that you did not understand, things you would be interested in? Yep.
So, I mean, is this just a general question? Is this whole demonstration will it be posted online later? So because
Yes. So this session is being recorded, and we actually on the LSSC TVSC YouTube channel have previous versions of this workshop as well, which are slower paced and also cover more. So depending on what you're interested in, you can look at those videos. So those are the videos you already have available. The HTML files, the workshop itself, the materials are also written in a way that's self-guided. So you don't really need the videos either. You just need an afternoon and you can go through all of that if you really wanted to. So all of this is public. And if you have any troubles at the end of it, we are always reachable by Slack, by email, and we're happy to help.
And Sid, maybe just to add on to that, I did mention that all of these materials are open source and free to use. So if you feel like you want to, teach your own lesson or to keep these materials for your own edification, or adapt them for your own purposes, please feel free to do so.
All right. Any other questions? We're only running 5 minutes late, so that's good. I can make that pace. So moving on, continuous integration. So we just saw how to write tests in general, how we can use tests, and that's helpful. And if your project grows larger, that's good to write, and so you can get a good overview of what's being tested, what's not being tested. The next step is, rather than doing this manually, can we do this automatically? And so that is something we call continuous integration, where the idea is that anytime you make any change, you want to automatically run your test. So if someone makes a change and suddenly, I don't know, your fundamental calculation goes wrong, you don't want anything else to go wrong, and you don't want to miss this. So if you make any changes to, say, your code, you want to automatically test that your code keeps working. And so we're going to use, for this, we're going to use GitHub. Git and GitHub are different. Git is the underlying technology. GitHub is a company that provides a service that you can use Git on an online way, in an online way, and then they have add-on tools. One of the add-on tools they offer is GitHub Actions, which for an individual user, it's free. You have a certain amount that's free to run, which should be more than enough for basic tests. So that's what we'll use. And GitHub Actions, essentially what that means is that if you push any code to GitHub, it will automatically run a test on their servers and test that everything works well. And so the way these actions are written is in YAML, where, if you're interested, it's called YAML Ain't Markup Language, and it's a recursive acronym. So the way you can read more details about this if you want to. It's meant to look more like human readable language rather than code, and so that's why its syntax is very human readable. So yeah, so that's the way these workflows are written in. So going back to our terminal, we can create this new directory. And let me clear this. We can create this new directory. Oops. Called .github/workflows. And you can see what that has done is create, it's a hidden directory because it starts with a dot. So if you want to ls it, don't forget the A, and you can see that it exists. So then the next part is, let me jump to my terminal, to my Jupyter, sorry. You can see that Jupyter by default does not show you the different hidden directories / hidden files, but there is a way to enable that. And you can do that by firstly modifying this file. So on your terminal, if you do a Jupyter -- paths, it shows you the different profiles it's looking at. It's configuration settings, really. And we can modify one of these to activate viewing hidden files. And so the way to do this is do a Jupyter server -- generate config. And so you can see that it generated a file here. I can open that. Sorry, Riley, I opened your VS Code. But depending on your laptop / computer, you can open it with a regular text editor as well. And the file you want to find is c.contentsmanager.allow_hidden. So it's something like this. I'm going to uncomment this and make it true. And so again, this is there in the tutorial as well. Once I save the file and I go back to my Jupyter lab, I can close this with the Control-C and rerun Jupyter lab. And that means that I will be able to now see hidden files and folders by going into the view section. And you can see I can enable show hidden files. So yeah, now you can see that there's a .github, which we just created earlier. There's a workflows, and we just have to create a main.yml. So that's the file that will trigger GitHub to automatically run code on their servers whenever you push something. So let me open that up, and I'm going to copy the YML file given here in the tutorial and paste it on the main.yml file. So let's just quickly go over it, where the name is just the name of the GitHub action. When does it trigger is what's given by on. So on push means that anytime you push something to GitHub, so remember that you have a Git that's on your system, and you can push it online to GitHub. And whenever you do that, that is when this sets of code is executed. And what does that involve? That involves firstly running on Ubuntu, checking out the repository using this action, setting up Python. You can see the version, you can modify the version, and installing all the dependencies. So that means a pip install, and then install all the requirements. And finally, running the same code which we were running on our PC. So it's a Python -m pytest coverage of FLC analyzer models on tests/test_models. So again, you're not expected to remember any of this or know all of this. This is not school, not college, so you can copy paste, and you can just edit whatever parts you want. So, but yeah, it's fairly readable. And once you save this, we now need to add it to our Git repository. So I'm jumping back into the terminal. I have this venv set up here, and you can see that if I do a git status now, .github has not been added. So let me quickly add this, git add .github, and commit it with added GitHub actions. And now it's been committed, but that's still on our end. So let me also push it where a git push should work. So a question for Riley. Do you know why this is not working?
So I think,
Is it this?
yeah, try that.
So I think what's happening is that the branch we are on is not on.
Yeah, so because our branches haven't been synced to the remote, I think is the issue.
I see. Okay.
Can you try doing a git fetch? Like git fetch -- all.
And then you're saying git push might work. I think you're right. I think it's related to the GitHub, which and I want to go to your fork, which is and test suite is what we're working on. I see. I think it's because, yeah, there's old code already, which might be causing it. So how about this? I'm gonna, in the temporary folder, pwd mkdir system. You shouldn't have to do this, and push should work for you because you don't hopefully have old code teaching this workshop before. So if I do this and do a git clone here, cd enter python git status, and now let me just copy the .github folder to here, and pwd lsa. Okay, I've added GitHub here, git status, git add .github, git commit, and added tests, and then git push. Okay, so once it pushes, and maybe I'm on the main branch, which you might not be on, but once you do that, if you now go to GitHub to your page where you have your fork, you can see that it'll show this orange dot with your commit as well from now. And if you click on these orange dots, that's GitHub running your continuous integration, aka the code you need to run the test on their platform. So now if you go to details, we see that there's some error because the Python version required is 2.5.1, which I think is a strict requirement. So let me open requirements. So I'm just modifying the requirements so that GitHub can open the same piece of code online. And I'm going to find NumPy, remove that. And so, yeah, essentially it's iteratively, this is why we run tests, so we can fix them one at a time. So again, I do a git status, I modify requirements, I'll git add requirements and git commit and update. Nope. And git push, not cut push. And let's see what the results for that look like. So this build failed. So this was one action. But now if you go back to the project, you see that I updated and pushed a different commit. And that's also running online now. If you click on details, you can track it live and see what it's running, what's happening, whatnot. And this now is really helpful because firstly, if you are not using Git for your software project, I highly recommend you do, because you can jump back in time, look at old code, easily merge, etc., etc. But now you can also use something like GitHub Actions, which allow you to test code automatically. So you don't have to worry about code breaking because of some typo, or if you have a cat which sits on your keyboard or adds stray characters. That should not make anything, stop anything from working, right? And so because of that, you can now have something like this running on GitHub. And you can see that even this, there's a small error where PyTest was not installed. And so we can go back and open .github.workflows. And if I open this with TextEdit, I can add a small install for PyTest, because GitHub seemingly does not automatically. So I think that might be because I did not add PyTest to the requirements. So maybe it's better to do that. So these are the requirements. You can add a PyTest. Now, again, the same as before. Git status, we see that we modified one file. Git commit, added PyTest. Git push. Wait, did it not commit? Oh, I forgot an A. And then git push. And that's pushed. And hopefully, now when I refresh this, that works. So let's see. Again, it's running. And so all of this is happening on the cloud, on the background. And in theory, you could turn off your laptop, go take a walk. And so it'll do everything in the background. So while that runs, let me go back to the lesson. And so this was the simplest test we did in this mini workshop, right? So we just triggered a build. We're looking at commits, does it work, etc., etc. But what you can also do is, instead of just testing it on one machine, you can also test it on the different Python platforms, different Python versions, sorry, but also different operating systems, where you must have seen sometimes that there's code that works on Windows but does not work on Linux, there's code that works on Linux, does not work on Mac, etc., etc. And one of the reasons we use Python is because it's supposed to be cross-platform usable. And so you can now test for each and every different platform which GitHub supports on their end and add them through this code over here. So I won't run this live now, but you can see how you can check for different Python versions. You can check for different operating systems, where here it's Ubuntu, macOS, Windows, etc. And so it essentially builds a matrix, and it runs the test for each combination of Python version and operating system. And yeah, so there is some other stuff mentioned here in the tutorials. Please do take a look. But hopefully, at least, we have motivated why you should test your code and how you can easily deploy it on something like GitHub and automatically test it. And even if you don't want to do that, you can always run it locally. And testing can help find you and spot bugs before you push some code which breaks anything. So highly recommend. We can wrap up. So here are the other resources. I know we talked about it a bit earlier, but there's a GitHub link for the full workshop, which is Intermediate Python for Astronomical Software Development. And that has a bunch of different resources that has multiple sections, including some of the things we looked at today, where there's unit tests there, but then there's also more about object-oriented programming and developing pipelines, etc. So all of this code is public. We also have a tutorial on high-performance computing. And as always, if you have any questions, please find us. And I think that's all from my end. I don't know, Riley, do you want to add something? Thank you.
Okay, so thank you all for attending this last session. I guess just to wrap up, I will post a link to just a short Google form on the Slack channel for this session. If you have any thoughts about maybe what went well about this mini course, maybe what didn't go so well, we'd love to hear your feedback in that Google form so that we can continue to host these workshops, both online and at future meetings, perhaps LSST Europe, LSST at Asia, who knows? Sorry for the hiccups with the Git branch issues, but Sid helped us figure that out with amazing skill. So yeah, I guess before we end the session, any last thoughts or questions about some of the topics we covered today? Okay, well, those materials are available for your disposal. If you would ever like to go back through it and maybe try some of the exercises, and hopefully, try incorporating test-driven development into your own research workflow and see if it works for you and your collaboration. So with that, I think we'll end the session just slightly early. And thanks everyone so much for attending.